Hi and welcome to Functional Justice in episode 14, and in this episode I'm going to carry on talking about adding effects to pure functional programs. In the last one we had 3 effects on the go, so we built a program to evaluate expressions, and the program itself used a data type that used the numeric type class, so that gives us the ability to implement lots of different numeric types. It handled errors using the either data type. It handled inputting data from an environment, so a symbol table. We did that using the reader monad. It could also log each of its steps, and that was using the writer monad. So between all those different things, we can build a program, and then we can add effects to it using the type system. And we saw that how combining these effects using monad transformers has some drawbacks, because each monad transform you adds sort of wraps the other one, like literally makes a class that wraps the other one. So it's eating up memory. It's difficult for the programmer to work with because you've got to continually lift things up and down. You've got to lift things up and then you've got to get inside the classes and get the data out all the time. So monad transformers can be tricky to work with. One of the solutions for monad transformers is in the form of MTL style. There's a library from type level called Cats MTL. It's a monad transformer library, and what it does is comes at the problem of monad transformers from a different perspective. Instead of having data types that represent each effect, it actually represents them as type classes. So you can build your program using various type classes, and then when you instantiate your program, you're going to give it actual concrete monad data types, but we'll see that even though it sounds like it's an extra layer of indirection, it's actually going to make things a lot easier to work with. Here's the Cats MTL documentation, and you can see that it's going to tell you about the library in much better language than I did just now, and gives you an example of what monad transformer code looks like, and you can see that that sort of lines up with what I was looking at last time as well. Just rather difficult to read, rather difficult to work with. And the nice thing about Cats MTL is that it takes these type classes, and you can write your program using these type classes in some abstract type F, and the type classes contain references to applicatives, monads, or functors. And this solves a problem that you can run into also with when you're using these kind of data types, that you might have an applicative instance of something, you might have a monadic instance of something, and the type inference doesn't know what to do because two of them match. With this approach, it can actually mix and match applicatives, functors, and monads much more easily without blowing things up. So these are the different MTL type classes that are available. So the names sort of are alluding to the actual monadic data types that they take over from. So instead of the reader data type, you can use the ask type class. We're going to also be using tell, which is going to be similar to the writer. Right? It has the same facility as the writer. It lets you log things. We've got stateful. We're going to use that too. Stateful lets you have read and write state. So if you want to read and write some state during your program, you would use that. And raise lets you raise errors, right? So that's what we were using the either for. And so if you're using an either or a monad error, then you can write code that uses the raise type class instead, and you'll get the advantages of it. And then later on, you can decide whether you want to use monad error or either. In the last episode, we wrote a program using monad transformers, and in preparation for this video, I've rewritten that program using MTL style. And the monad stack looks like this. So we've got a either t on the outside to handle errors. We've got a writer t, which is going to handle our log. And we have a reader in the middle, which is going to handle our providing our symbol table. So that's the environment events. And then the actual computed value, a, is going to be has to be a subtype of numeric. So that's essentially the data type that we used in the last program. So now we can go and look at the new code. So this is the program converted from mono transformer style to MTL style. So I'm just going to give a quick rundown of what this program looks like, and also what it does in case you didn't watch any of the other videos. So firstly, I have my own numeric type class. So the reason I'm using my own is just because the built-in Scala type class doesn't behave exactly like I wanted it to. So for example, it doesn't have divide in the numeric type because well, for mathematical reasons. You have to go and look in the source code to see why. But I just wanted to make a numeric that had these 4 basic operations just for the just for demonstration purposes. Then we've got the numeric type class. Remember that type classes have an interface that's defined using a trait. Just should point out that I'm using Scala 2 for this video. Cats MTL does support Scala 3, but when I was working on this initial project, it wasn't ready, and I was using Scala 2 instead. So this is the type class itself. It has instructions. It has an algebra for adding, subtracting, dividing, multiplying, and it also has this predicate to tell you if the number is 0 or not. And then we have instantiations or instances of these of the numeric type class for integer and long. You could write this for other number types, and you could write it for your own mathematic types. You could write it for Roman numerals. You could write it for long binary strings. That's the whole point of using a type class instead of just building it for one specific number type, and then you're kind of stuck with it. So when we deal with errors, we've got 3 types of errors to worry about. Sorry, we have 2 types of errors to worry about. They're all of the same type error. So symbol not found means that our expression couldn't find a particular symbol it was looking for, and then division by 0 obviously means we tried to divide something and it failed. This is the type of our lookup table, so it's literally just a map of strings to type A. Here's the ADT. This is the abstract syntax tree for our expression language. So we've got add, subtract, multiply, divide. We also have var, which is the variable lookup. So we can make expressions with strings, and then we'll look them up in the environment that's passed in. And then we have values, which are like literal values, literal values of A. I'll come back to these operations. We'll just look at the main loop of the program. So the main loop of the program is an eval function, and the eval function, now we're using MTL, needs an abstract type F, and it needs the return type A, which must be an instance of numeric. And then it takes as its main argument the expression that you want to evaluate. So we'll see what an expression looks like below. Now what we do here is, to use MTL, when you're building a function, you must give it a list of all the type classes that you want it to use. So in our case, we're going to be using all of these ones. So we've got tell, which is our writer. It gives us the facility to write a log while we're doing our computation. We've got ask, which is our reader. That's where our symbol table will come from. We've got raise, which allows us to raise an error if something happens. And then we've just asked for a monad explicitly because in some of our code we need to use flat map. So what I'm doing is, by putting this here, I'm saying the program must have a monadic instance of each thing, otherwise we won't be able to flat map things. Now if you don't need flat map in your program, you could drop this down to applicative or just leave it out completely and let the user decide at runtime. So here's an example expression. We're just multiplying something. We're going to add something. We're going to subtract things. We're going to divide things, and then we also have a symbol table, which is a simple map of symbol names to integers. Before we can run the program, we need to give it a we need to materialize the program by giving it a concrete type to work with. And all we need to do to really do that is tell the Scala compiler what type we're using. So we're going to be using this either T, writer T, reader. So it's 3 levels of nesting. Now this still looks ugly to have to define this, but it's a great improvement to only have to worry about this type at the edges of your program, and then the actual code that you're writing looks a lot cleaner because you really don't have to worry about it. To actually run the program, we need to create we need to call value on it. So what we're calling value on is the either. So let's see, program itself is an either. When we call value, that will give us the writer reader, and then we pass in the environment by using the run, and that will give us the final result, which is this tuple. So the final result of the program is our log, is a tuple of the log, and then the result of the program, which is going to be either an error or an integer. So let's just run the program. So you can see the result of the expression is 1100, and then you can see the log of the program that was created when we ran it. So let's see what happens if we had an error. So let's say that the division part here, we're going to divide 20 by the value of y. So if we make y 0, then we should get a division by 0 error instead of the success result. There you go, failed with error, division by 0. So another error we handle is symbol not found. So let's say instead of Z we had an A. Let's go and run the program with an invalid symbol. And there you go, symbol not found. So next I want to look briefly at how the functions themselves are implemented to build this program. So first thing is literal values. In order to get a literal value, we just need to get a monad and call pure on it. So remember, we instantiated a monad, or rather we said that we have an implicit monad m. So we can just call pure on that, pass in value, and that will give us the result of the right type. Handle variable, this has to do a lookup. So now we're going to use the reader. So we've got in the implicits here, we've got our reader ask. So we can just do r ask, and that will give us the symbol table, and then we can flat map over that to see whether we have a value or not, and then that's going to give us a either. We're just using the Scala built-in map lookup there, which gives you either an error or the or it finds the value. So you can see that if we find the value, then first of all we're going to write a log just saying that we found the value and what it was, and then we're going to wrap the value using the monadic pure operation. Now if you're not familiar with this symbol, I think it came up a couple of times before, but this is essentially a shorthand for a flat map where you're not interested in the result of the first thing. So if you look at this flat map, we needed to get the value from it to carry on with our next monad, but in this case all we want to do is say take this monad and then sequence it with this one. I should also point out this might not be a monad, it really depends on your types. If this wasn't a monad here, this could be a functor or an applicative, in which case you wouldn't be able to flat map over it. Anyway, so that's our variable lookup. I won't look at all of these four operations because they're all the same, but let's look at addition. So what we have here is to handle addition. We've got the same type signature as before, all the different effect types we need, all the type classes we need, and then we evaluate the first, the left hand side, because that's an expression. Then we flat map that, which will give us the resulting A of that expression. Then we evaluate the right hand side, and then we're going to flat map over that. And then at this point, LA and RA are the left and right hand side actual values. And then we can create a log entry, and then we can lift them into the monad using pure again. So I think the code is a lot clearer than when using monad transformers, and in general they're easier to work with. What is a shame is you still have these very long type signatures. There's not really much you can do about that. Although it's possible that you could use Scala 3 context functions to help with that, because you would then just need to put one type definition at the top of the file, and then use context functions to infer all of the different things that you need. In fact, I have a feeling that context functions and this style of monad transformers, the MTL style, could be quite fruitful. Anyway, so just to show how these are actually easier to work with, the next step is to add state. So adding state to what I did last week would have been very difficult, because we would have had to introduce another layer of monad transformer, and our code was already getting very difficult to work with. So I think you'll find that adding state using MTL, or not adding state, but basically adding another transformer type is much easier in the MTL style. So I think MTL style gives you code that's a lot more scalable in terms of complexity. So what I'm doing here is I'm going to use the Stateful type class, and as an example of state, what I'm going to do is one of the things I was working on recently was evaluating an expression and trying to figure out what the cost of the expression was. So in other words, different operations cost more based on the real operations they do, but also they cost more based on the ongoing computation. So if you've already looked something up in a database, for example, doing that thing again is actually much cheaper. So you can use these kind of techniques to make your code analyze itself, and we're going to do just that. We're going to add a cost to each of the expressions, and then our mutable state is going to keep track of how much the expression cost, and at the end we can just print that out. So the first thing I need to do is all the functions in my program need to have the stateful type class as well as these other ones. So let's just do a search and replace to add that. So wherever I have eraise, I'm also going to have a new stateful of type f, and then it has a state type, which is just going to be an integer, because we're going to accumulate the cost of all of our things. Okay, so that should work. And now the problem is that the type that we materialized here to run our program doesn't have state, right? So if we look at the error, couldn't find an implicit instance of stateful, and you can see that the error message is helpful. So it's telling us that we need a type like state t, and in fact that's exactly the type that I had in mind. So I'm going to go ahead and add state t to this this type, and state t takes 3 arguments. So it takes a monad, which is essentially going to be the rest of these things, the writer and the reader. That will be our first argument, and then it takes the state type, which is going to be an integer, and then we'll have a wildcard for the computed type a. So I can do that by just increasing the nesting here. That's the monad. This will be the state type, and then this will be the wildcard for the type. Alright, so we fixed the program. Now our problem is that we have a type mismatch. We should have an integer here, and that's because we've changed the structure of the program now. It used to be an either t, writer t, reader t, but now it has this state in the next part. So we need to pass in some initial state like that, and now we're good. And now we just got to fix this part because the run result has changed. So now you can see the run result is actually a tuple of the log, and the second part of the tuple is another tuple, and that has the state and the actual computed result. So now this needs to be the second part of the second tuple, which is the actual result, and what we can do now is also print the final state of the program. So the state of the program is run result. It's the first element of the second tuple. So if we look at the run result again, you can see the second tuple contains the state and the result, and we want the first tuple of the second tuple. So now we can run the program. We got it compiling again already. And oh, I forgot to fix the symbol not found error, so that should be Z, not A. So run this one, and then you should see the computation basically succeed with a log. And you can see that the state is being passed all the way through the program, but it's just 0 because we didn't yet implement any state. So now all of our functions have access to the stateful type class. So if I want to add some state, all I need to do is do s set and pass it on to the next element. And sorry, actually what I'm going to do is modify. So modify gives us the ability to get the current state and modify it. So the current state is going to be our integer, and then what I want is for values to cost 1. Literal value is the cheapest thing, so they just cost 1 like that. So now when we run it, whenever we evaluate a value, a literal value, will increase the state, will increase the cost of computation by 1. Now variables, let's just say they cost 4 because it's sort of analogous to some kind of lookup. This is all made up stuff, of course, doesn't really have a lot of bearing on real life, but if you're doing this for a real business domain, you'll probably have much better idea of the cost of each component. And then maybe add, subtract, division, and multiply will just make them 2 to indicate that they cost more than literal values and less than variable lookups. So I'm going to go ahead and run that. And there you go. So the result now is the same as it was before, and the state is 25, which means that we were able to evaluate as we were working on our program, we were able to calculate the cost of it as well. So as you can see, it only took a couple of minutes to add another monad. Now, if you were working with monad transformers, you might get into type hell, and it's going to take you like 10-20 minutes or more just to get it compiling again, and then your program is much more difficult to work with, because when we add an implicit type class here, that gives us an extra piece of power that we can use in our functions, and it's really easy to use, right? And the fact that we're using this, this is actually known as final tagless approach, where the result of your program is an abstract type. So final tagless is loosely defined as a sort of an algebra that's defined to be an abstract return type, and at the end of the program, or rather the beginning of the program, that's where you instantiate the real concrete value of the program. And yeah, so that means your program is flexible. You can use different kinds of effects, and you can swap them out whenever you're ready. Okay, so I had a lot of fun learning about MTL for this video and making this little video about it. So I hope you enjoy it, and if you did, then make sure to smash that like button and share this video with your friends. Thanks a lot. Bye now.